All right, welcome back to another video in the Machine Learning for Network and Cloud Engineers series. So we're on to a kind of meteor section in the book. I don't think I pasted this graphic into ChatGPT yet. It's pretty faded, so I can't really see it too well. Let's see if ChatGPT can see it and has anything to say about it. Now I've done I started a new series on a home office setup, and I'm going to need to do a series on headphones at some point. I so my headphones I've got a lot to say about headphones. I think they're perhaps some of the most important things you can have in your office because when things are noisy, you can go and yell at your neighbors, or you can shut the door, but there's a point where you really just can't do anything. If there's planes overhead, if there's a leaf blower crew, all you can do is put on a pair of noise canceling or noise reduction rated headphones. So I've got a lot to say about that, but the reason I'm bringing it up now is because we won't be able to hear ChatGPT read it back because I'm kind of going through swapping out to a different set, which I will talk about in a later video. But for now, so yes, this is a network architecture diagram, and I just want in a fun and engaging way, just to know some basics about it. I just want to stay engaged and not be bored to tears and fall asleep when I'm learning about this stuff. So we can't really hear it. Oh, that's cool. All right, so you can think of it like a museum. Um, yeah, but I don't have my headphones working right now, so uh, it'd be kind of difficult to get that output. So let's just continue on. The other thing is, I had all of this working locally, which is really awesome. So I'm going to get this up and working locally again, and we'll run all the code to where it was again. So I need to start a Jupyter notebook, and I can close the other port that's just lingering open. And now all I need to do is start. And I had to do a lot here. I had to work with ChatGPT to get this working. All right, so but now we've got the Jupyter notebook. We've got the one that I modified, and we can see using the change management tool here the changes I've made so far, including to the notebook here. So we can see I've made quite a few changes, especially to the local, especially to the outputs. Of course, the outputs are going to be different, but I had to change all of the because I'm not using Google Colab. Now, for anyone watching this, I do recommend you use Google Colab. It's just a better thing to use. You get free GPU time on it too. So if you don't have a nice computer, don't worry. Just use Google Colab. And even if you do, you might want to consider using Google Colab. I just kind of, I'm that guy. I just wanted it to work the way I wanted it to work. I have a nice GPU, so I just wanted to use it. So now we see that um, the numbers are here for which cells have run. So let's look at the last cell that has run. All right, so this is the final cell that has run. So the next cell will be here. It has that find me there. Um, and yeah, we'll be running that later as we go on. In this representation, we can also see what are the activation functions used in each layer. TAN-H is used in the LSTM layers, and there is no activation function on the dense layer. Because we are trying to do a regression, not classification, we have no activation function as such. For the dropout, they are not really real layers. Simply instruct TensorFlow to activate dropout in the previous layer and repeat vector and time distributed are also artifacts simply to replicate data or a model respectively. Let's pay attention to the model compilation command. In the compile method, we can specify multiple parameters about how we want the model to be trained. In this case, we are specifying the loss function MSE, mean squared errors. There are other types of loss functions which are dependent on the use case. The optimizer determines how the training process will happen and how weights will be updated in each iteration. Each iteration. In our case, I am using the Atom optimizer, which is a very common option. Also, I'm specifying which metrics I'm interested in the model to generate during training. Those metrics will be used to determine actions during the training process. So here's the next line. It's model.compile. So, interesting. Where's that? Well, I guess I'll search for it. Model.compile. Oh, okay. So it looks like I'm a little bit ahead. So this was the 39th line that I ran. So I'm a little bit ahead, I think. There are a few other options we can define around our model that will help controlling the training process. So file path, checkpoint, callbacks underscore lists. Let's see if I'm there. So yeah, here's the next one. So I'll run this cell. And join is not defined. I think that's because the prior ones haven't been. I'm tempted to just want to run it again. But let's do join equals. Nope, sure enough. Let's do. Okay, yeah. So join would be defined here through the import statement, but even so, all we've got here is the output. We don't have the actual code loaded up. Like the kernel is not loaded up with the variables. So join was not defined because of that. So unfortunately, we do have to restart and clear the output, and then run each of these cells again, which really sucks. I'm actually not that big of a fan of this. It'd be cool if I could like set a breakpoint. I'm not a big fan of Jupyter notebooks. They're good if you have to see like a lot of graphs. So like it makes sense that they do it in data science. But I mean you can see it in I'm pretty sure you get the graphs here. Well, it looks like you don't. Oh yeah, you do. See, you get the graphs here as well. And we had an extensive conversation with ChatGPT about that, and it's valid to use either one. There are some advantages and disadvantages, like always. So it makes sense that like Jupiter is definitely a good choice. It's kind of a matter of personal preference to an extent. All right, so then this join here wasn't working, so we'll wait for things to get here and then run this. In the meantime, let's read some more. A checkpoint, and I'll advance the bookmark just in case. A checkpoint will help define the conditions by which the model weights should be saved during the training process. This is extremely useful. The training process may fail at any point in time. It may crash, your Google Colab connection may disconnect, etc. There are a large number of reasons by which your training process, which may take minutes, hours, days, or even longer than that, may be interrupted, and you definitely do not want to lose the state weights that have been computed so far. The checkpoint in this case defines what metric we need to monitor, MSE, the mean squared error, when to save new weights in the file, save best only, what condition to satisfy that the metric we are monitoring is lower than the previously best one, and which file to save the weights to. With this, we can have the peace of mind that if the training process is interrupted at the minimum, we have the weights saved that correspond to the last best set of weights that were computed based on the indicated metric. Then we can always load those weights back to the model and start the training with those weights initially, which is sort of equivalent to continuing the training where it left. That is not exactly accurate, but we can use that intuition. So model.loadWeights path. So now we're continuing where we left off, which isn't exactly what we're doing, but it's similar. At this point, we are ready to train the model. We have the data, we have the model compiled, and the checkpoints in place. All right, so we don't have that. We're waiting for things to run. And okay, so now we're there. So let's get those checkpoints in place. So we need to run the code down to this history equals line. So yep, down there. Oh, got a problem here. Okay, well, that seems like an easy solution. There we go. How's that? Oh, I don't know what happened. It did something unpredictable. There's an empty cell. I will cut out that empty cell. And then this cell didn't get run. So I guess I'll run this cell again. And then this cell. And then run this cell one more time. Yeah, so it's the wrong thing. So now this is 2 dots. So hopefully I can do a Control Z. I can. Okay, perfect. So I'm going to do KERAS instead. Okay, there we go. So now that's working. So we've got our callbacks list with our checkpoint. And oops, so we've got no file or directory. So I guess we can see what the path file is here. Our file path. Okay, that looks fine. And it's saying this all matches, UC1. Interesting. It's saying that there's no. Well, that doesn't make any sense. There is. It's right there. What? That doesn't make any sense. Um, you know what I'm gonna do? I think I'm going to advance the find me. Put it on this cell here, and then run all the cells again. Okay, so then there we go, and then I'll pause it. I'll be right back. I need a quick break. All right, I'm back. So let's see where we got. So, yep, we got all the way through. Now we see the file is there. So let's what the heck? That's not true. What? WEIGHTS. I mean, it's the same variable. I can't load the weights in. Well, I mean, it wasn't the right file, right? Yeah, so it needs to be an HDF5 file. But it can't because it has to... It has to be in that model format. What the heck? No such file or directory. That makes no sense. You know what? I think this one is really good for ChatGPT. ChatGPT is good at this sort of thing. So we're going to screenshot it. We're going to put it in, and we're going to say, this makes no sense. So this makes absolutely no sense. Like, you can see it's just that one variable file path. So, like, how does it not... How is there no such file or directory when I can print that file path out? Like, that the variable got successfully defined. So, like, why is there no... Like, why is not a valid directory or file? Yeah. So, okay. Yeah. Right. Yeah, we did that already. Oh, yeah, maybe the join function didn't work. Here's a step-by-step investigation. Okay, so... Oops. Yeah. Path files. I guess maybe this is where it goes wrong. Path files? What does path files equal? Uh... Okay. No, path files is right. Oh, you know what? Uh, I don't think we're getting file path. I don't think it's creating the file. Yeah, that's what's happening. Is like it didn't create a checkpoint. Like it has the file path. And it knows like what to name it, but like something's going wrong with this where like it didn't actually create the checkpoint. Because if we were to do a print checkpoint down here, oh my god, and run this cell again. Uh oh, okay. Callbacks list equals model dot load weights. Okay. What? So obviously it didn't get. Obviously something happened where it has the file path, but it didn't. And let's look at path files again because that might be a. That. Oh, you know what? It's probably as stupid as this. I think that's probably it. Okay, so another thing I could have done is I could have added it here, but it's just when it joined these together, it joined it all as one word. I think so. It if we were to actually like list out that, which we might actually see somewhere. Um, yeah. So in the source control, there should be. Well, yeah. Here we go. So uh anomaly model. Well, I don't see it. Shoot. So, let me take a quick pause. I'll be right back. Alright, and I'm back. And let's take a look at the results so far. Okay, so we're here. So I think it was as stupid as that. Let's try it. Nope. Okay, well, good. That would have been kind of annoying. So, yeah, so we can troubleshoot here. So we see the problem is, so we do have a checkpoint that was created correctly. We do have a file path that was created correctly. We can see the file path here. So it actually wouldn't have been the problem that this join statement failed because we did see the file path was correct. So it's just not able to load in the weights is the problem. And it's not able to load in the weights because it can't find the file or directory. All right, so let's comment this out for now. And let's do a help on it. And then run the cell again. Okay, so now we get the help. So load weights, file path. This is a a path to the weights file to load. It can either be a .weights.h5 file or that. So it's not named correctly. So we're gonna name it uh, weights.h5, and then comment this line, and then uncomment this line, and see if that fixes the issue. Okay, so now we've got the same kind of problem. The file path must end in .keras in order for it to be used as a checkpoint file. So let's do this. Let's have it be the file path here, like that, with the .keras just as it likes. But then we'll redefine the file path so that it likes it. Yeah, so we'll be like that, and then we'll redefine it down here. Okay. Oh, so we got the same problem here. So we do have the weights.h5 now, but we've got that same unable to synchronously open a file now, which makes no sense. All right, so let's do this. Let's print out the working directory. That'll probably open up a lot of. Um, that'll be pretty eye-opening. Okay, so yeah, that's fine. But do we have so os dot ls? Is there something like that? Is there listdir? Let's try that. Contents. Then we'll do print working directory, and then we'll do print contents. Okay, so we've got some files in here. We don't have the keras file in here, which is interesting. Yeah, so we've got this .keras file, and then we feed the file path there. This is number 2. Where's number 1? 2, 3. But I don't see the fourth one. Okay, I guess it's just finding it in the find bar. All right, so this is the first time this pops up. Now the thing is, I think what we're doing is we're creating a checkpoint from the existing file. So it's not going to be called that. It's going to be called what it was called before. So let me try to get back to what it was. Yeah, so it's waits autoencoder auto MSE best. So it should end with the word best. Yeah. And this is auto instead of dense. Yep, that. So yeah, it's actually trying to interact with this file. So if we don't call that file, then yeah, it's not gonna work. So I guess what we could do is try renaming that file. So if we go here, we run it, we're gonna get that same error where it has to end in .keras. So I guess we can try that. So let's try to rename this to .keras here, which is, yeah. So this is how you would actually do that before I messed it up. Okay, and then to try to make sure that this change goes through and is reflected in our kernel and notebook, I will restart notebook, open it in browser, and then not save anything, go back in, and now we can check it there. We could have just renamed it from here, but this works too. So I'll clear and restart, and then run everything again. All right. Now I don't know why these are on 2 lines here. That's kind of odd. There's no option to have this one run. Is it because of the print statement? No, it's just, I don't know, maybe it's a bug. All right, and similarly, I'll take a break. I'll be right back. All right, so let's see how we're going here. So yep, we're all the way down to the find me. So here's the moment of truth. Right here is the moment of truth. And there we go. It was able to do it just fine because I changed the file to .keras. So yeah, we're ready to go. Let's do so. Let's go back to the book. So we're going to do load waits. Let's go to the bookmark. Yep. So we're going to load waits, and then the history equals. Yep. So this is the last one. There we go. Epoch 150. So yeah, all right, let's keep going. And this is where the magic will happen. This command triggers the training process. Usually the first 2 parameters are the training data in the form capital X, Y, the data, and the labels. Because our intent is to train this model as an autoencoder, we use capital X instead. So the label is the same as the input data, capital X. Once one epoch is a complete iteration over the input dataset, there will be the need to go through the dataset a number of times to train the model. How many is completely dependent on the specific use case. You do not know in advance. You can set callbacks to terminate the training process if the performance of the model is not improving by a certain percentage, for example. In our case, we have set 50 epochs, and We saw that here. We saw all the epochs that were set, 50, and this is cool. We can actually see each of the epochs working here, and it seems to be working quite well, which is pretty awesome. When we train the model, we do not push all the data at once. We split the data in batches, so we save memory and accelerate the training process. This is also a hyperparameter to choose the size of the batch. A larger batch will trigger more complex and longer and resource-intensive computations, whereas a smaller batch size will eventually result in more inefficient and potentially worse conversions. So we may need to try some values to find the optimal one for our use case. I am using a value of 128. We have also activated validation, which will automatically pick a certain percentage of the observations and use them for validation. When we execute the .fit method, the training process begins and will look something like the following capture. Okay, so I already executed the training process. Let's take a look at that .fit method. Okay, yeah, so I executed that here. We can still see it's still working, and we can see we're on epoch 15 of our training here. There will be times where the weights will be saved because the metric MSE, which is the mean squared error, that's the metric we're using, is improving with respect to the last best value. As you can see in each epoch, the loss and MSE are progressively improving. That is because the model is converging to better weights. Also, we can see the validation loss and validation MSE, which are in this case most of the times better than the training ones. The likely reason is because we are using dropout in the training, and that makes the training more difficult. So when validation is done, which does not use dropout, the results are better, and that is what we want. Be able to generalize better for data not seen before. So we should see, we should see our metric improve. So we've got the MSE, so it improved from it's not defined yet because this is the first epoch. So now it's at half a second, and we see it continually improving. Now we're on epoch 22, and epoch 22 is at half of a second, so it improved by a factor of 2 there. So, and then we should see training data later. I think I'm not sure if we're at that yet. But let's keep reading. Once it reaches the number of epochs predetermined, the training will end. You can decide to initiate the training again with the same weights, so effectively continue the process. If you feel there is still room for improvement, simply run again the .fit method. Usually the first epochs will show a significant improvement, but you will observe how such improvement decelerates or even eventually almost stops to the point where there is no benefit in continuing the training process. Also, the model might not converge at all, which frequently happens, so you will see that the loss does not improve, or sometimes improves and sometimes gets significantly worse without any clear trend. That is a sign that we need to get back to the whiteboard to redesign the approach or the model. It is possible to visualize how the evolution of the training process went across the different epochs, and it is very clearly visible where the points are beyond which more training might not be useful. When we executed the training, we assigned the output to a variable called history. Such history is a dictionary with some keys we can explore. So next line here, we're going to list all the keys available in the dictionary. So this will be the plt.show, and we'll see a graph of the training. But right now I'm on epoch. Let's see here, 34. So we gotta wait for it to finish training before going on to that. So let's try to get as far ahead in the reading as possible in the meantime. We can see how up until epoch 20 approximately, the training MSE was improving, but then it stalled. Interestingly, the testing or validation MSE still kept improving, probably because the continued training with dropout. Now we have the model trained, we can use it to evaluate or predict values. The following commands give us various options to evaluate the model. So here we go, various options to evaluate the model. We can use the model to generate predictions for all our input data set, and we will pick up the last value for each prediction. Let's keep in mind that the model is generating a whole 72 by 1 vector. All right. There we go. So total anomalies.head, which usually shows you the first few lines. In the above visualization, we are capturing the difference between the predicted value and the actual value of the metric. Effectively, when the loss is high, that means the metric is not behaving as the model has learned, so it can be considered an anomaly. We have computed a threshold as the 99 percentile of the loss values, so we consider that being the point beyond which a point will be determined as anomalous. All right, and I'm, as I said, I had another home office video, and I'll do more on that later, but for now I am using some of my home office here. We can then visualize the data as we have done with the previous models tested and see the anomalies we detect. All right. So we're going to see the anomalies. There we go, graph of the anomalies. The reconstructed metric is following quite well the patterns, and there's another and there, that's a typo. We can see that the anomalies are not really influencing the constructed metric, which results in a quite smooth graph. It is detecting quite well the anomalies, but it is also triggering false positives with high values, where the reconstructed metric is not reaching the higher values. If we revisit the way we have trained the model, we have used sequences of 72 observations, which means 6 hours. That means the model is never exposed to a longer sequence that allows it to learn the seasonal behavior. So it is reasonable that it is not capturing longer patterns that would result in more accurate values. You may try yourself with longer values for time_steps, but you will see that this does not result in a good outcome, probably because LSTM is struggling to capture such longer term patterns. 7 days means 2,016 observations. In these situations, we can try a different approach with an autoencoder based on dense layers. Ultimately, even if what we have as input is a sequence, we can simply consider it being a vector. So ignore the time aspects of it. We could build a dense-based autoencoder and see if it is better at capturing the seasonality and other patterns in the data. All right, so let's see how far along we are. Uh, we're on to epic number. Oh, so we got everything. It did not improve. Starting at epic or epoch. Okay, so it's improving, and then at epoch, it looks like epoch 18 it maxed out and it stopped improving from there. So that was pretty early on, which is kind of surprising. Yeah, it looks like. Oh, you know what? It looks like every once in a while it did improve. So that's interesting how that works. All right. Anyways, moving on to the next. So we're gonna see all the graphs that we just read about. Okay, and remember, we have this issue. Yeah, so we have to. So now what we're gonna do is we're going to save it. So we have to save it using the right syntax or using the right file name. So we're gonna name it .kara. Oh, but there's still it has to have an S. Okay, and there we go. Here's all the history of the keys. Here's one of the graphs, so we can see how the training, it leveled off around 12, and then, it kind of had an interesting spike there. I'm not sure what that's all about. That's around epoch 40. Let's take a look at it. So, yeah, it kind of stopped improving around there, and not sure what that spike is all about. Maybe it's one of these other values. Yeah, okay, I think I see it. The val MSE kind of spiked up to 0.06 and then went down. So I think that's what we're seeing there in the graph. All right, so on to the next one. Here's the next graph. And then model.predict. Let's see how far we got to go in the. So we got to go to time.steps. Okay. Let's get so accuracy score. I'm not sure what that means, if that's good or bad. Let's see how that compares to the accuracy score in the book, if it's there. So I think it's here. No. Here it is. So accuracy score 0.06 for test score and test accuracy. So let's see what I got. So I think I did a lot better. I mean, I don't know what these numbers mean, but my number is higher by a factor of 2. It's double what their number was. So I think that's good. I don't know. Could be bad. I do have a really nice GPU on here. I can run basically any game on like ultra settings. Because I game so much, obviously. Just in the extra 5-10 hours I have between these videos and work, all I do is game, right? I don't sleep or anything else. I'm just kidding. I really don't game. Anyone watching this who yeah, well, it's not time for this talk. At some point, I might have to have a talk with my audience about if you're kind of addicted to gaming and not doing what I'm doing, like reading books and learning, and you're dissatisfied with your life progress. Well, maybe therein lies the problem in some ways. I think it's important to enjoy life and to do things that are meaningful. If that means gaming, that's fine. But you have to balance. There has to be a balance. There has to be, anything is good. Anything is fine in moderation, including moderation. All right, so here's a graph. So we got more graphs to come here. So this is the graph here. So we need that multicolored graph as well. Here it is. Now it seems to be quite a bit different. Which line do we have to go down to, actually? Oh, feed forward? That's probably the last one. Let's see here. So model.compile. Oh, so we should get a we gotta go to model.compile, which is probably the last one. Model.compile. Oh, yeah, so this one. I'll move the find me down here. All right, so that one's completed. We can see that by the number there. That's just an easy variable definition. This is kind of more advanced. So we've got graph there, or chart there. There, here's one of the graphs. Now we can see that I think this is kind of going wrong a little bit, because we can see the threshold is pretty messed up. I don't think it should look like that. I think this is basically like this graph, actual BNG, DS, anomaly. Well, no, this is the loss in the threshold, so this is a different one. I'm not sure which one this is. Oh, it's this one. Okay, so yeah, everything's looking good so far. Perfect. Yeah. All right, and now we've got the graph I was expecting. So yeah, things seem to be going very, very well. Honestly, probably better than what we see in the book, because we had that accuracy score, which was twice as high as the other one. All right, so now let's get down to the find me. Yeah, so here's the timed out steps. So next in the notebook, therefore, I have added another example of defining a new model and using a longer time_steps variable extended to 2016, which corresponds to 1 week worth of data. We will be training the model with sequences that represent 7 days of BNG_subscriber metric, and we can expect that the model may learn more in depth the internal structure of the data with the autoencoder. Okay, so it wants to run everything down to, so now it's time to run everything down to this cell. So this one's taking quite a bit. There we go. There we go. There we go. And now the cell of the day. Oh, so we got a problem here. Do not pass an input shape, input dim argument to a layer when using sequential models. All right. Prefer using a, and you know what? It's just a warning. That's okay. We can ignore warnings especially for now. There. So now we do get the model summary. So that was just a warning, and everything worked. The following diagram captures more visually the type of network we are using in this case. So I am going to feed this to ChatGPT. Even though I don't get audio output right now. I mean, I could get it through my. Let me do that.
This image illustrates an add-on coder architecture, a type of artificial neural network used for unsupervised learning of efficient codings. Let's break down this architecture in a fun and engaging way. The journey through the add-on coder, Imagineer, and Explorer on a quest to find hidden treasure, valuable insights, in vast landscape data. Your journey involves two main stages: encoding, compressing the map, and decoding, reconstructing the treasure map. Stage 1. The encoder, the map compressor input matrix. Description. You start with an input matrix of size n times 2016 times 1 n times 2016 times 1 n times 2016 times 1. Here, NNN is the number of observations, and each observation is a vector of size 2016. Visualization. Think of this as a huge detailed map with NNN different routes, observations, each route having 2016 steps. Layer 1 dense, 1024. Description. The first stop on your journey compresses the map into a smaller version with 1024 steps. Features. Visualization. It's like folding your big map into a more manageable size, highlighting the most important paths. Layer 2 dense, 512. Description. The next layer further compresses the map to 512 steps. Visualization. Now your map is even more compact, focusing on only the most critical parts. Layer 3 dense, 128. Description. The final layer in the encoder compresses the map to just 128 steps. Visualization. You've distilled your map to its essence, capturing the core features needed to find the treasure.
Okay, so now there's a problem. That's okay. I'm not gonna. Sometimes I feel like this is a little bit of a waste of time because it just kind of goes in one ear and out the other. But let's continue on. So the notebook follows the same steps as we followed earlier on the LSTM-based autoencoder example, so I will not repeat them. Let's review directly the results and how they look like. So here's another graph here. The results are not substantially different. It is quite good at detecting anomalies. Some are missed, but there is definitely some fine-tuning that can be adjusted. Like in the previous case, the model is still not able to capture the peaks more accurately, and for that reason, it is detecting as anomalies most of the values at the peaks. So we've got anomaly detection. So yeah, once it peaks, that's an anomaly. And that's because it's not able to capture the peaks accurately. Let's see what mine did because I seem to be working with a bit more horsepower here. So, yeah, mine's not just calling out all the peaks. We've got some here that aren't peaks. That's pretty cool. Now that's I don't know if that's the graph that we're talking about here. Oops, and you know what? Okay, yeah. So we're moving on to dense now. So I think we're talking about this one. So, unfortunately, I think I have to change the file, and then I have to, yeah. So if I change this to Keras, now I have to go and change it here as well. So, yeah, right here. And I think I probably do have to restart everything. I don't know. We'll try it. Let's try it without restarting everything. Oh, you know what? It worked. Cool. Okay, so now we're training it using dense rather than auto. And we should see I guess the point of that is that even though you're using dense rather than auto, it still won't be much better. But I think mine did a lot better than theirs because if we go back to the anomaly detection graph for auto rather than dense, no, it's about the same. There's a lot of them in the maxes here, but yeah, I think it's quite a bit different. I don't know. Yeah, so we're training it again, this time using dense rather than auto, so that's going to take a bit of time, so let's keep reading. Takeaways, some key learnings from this use case and the approaches showcased that I would like you to take. Anomalies are always very contextual and to some extent subjective, so all methods will require fine-tuning of some kind of thresholds where you express your anomaly tolerance. If data changes, the anomaly detection technique required may also need to change. No one size fits all. There is a wide range of models with different complexity that can be applied to a problem like this. We need to be smart in choosing the right one, and that includes, among multiple factors, the explainability. Neural networks require a lot of data and are expensive to train. Further work. This use case could be improved, definitely, by fine-tuning the models we have used. These are almost presented in their default parameters in the notebook. There are multiple other algorithms that could be used as well, but we could also evaluate the strategy to use ensembles. As we have seen, some models may be good at detecting some anomalies and others and not others. You could think of an ensemble approach where several models could be used in parallel and use a voting approach to determine if a sample is or not anomalous. These are just ideas of further work in case you want to explore any by yourself. And I might, I actually do want to. I want to create my own set of hands-on exercises. So, that, you know what? Let's bookmark this because let's highlight this because I do want to come back and work on my own set of hands-on exercises. So use case 2, are my SD-WAN edge devices behaving as expected? So this is obviously a stopping point for this video. We're probably at the hour. We're past the hour by almost 2 minutes here. So we're on epoch 50 is now completed, so we're all the way done. So we can look at the graph. Okay. And we can print out the rest of the things in this notebook. We've got a problem here. The file name must end in .weights.h5, and so we did that before there. So interesting. Model.saveWeights. Oh, you know what we did is for the checkpoint file we used Keras, and then afterwards we renamed it. So let's use that same strategy here. So we're gonna redefine the file path specifically for this cell. And then we'll use that proper naming. So it'll be weights.h5. And we'll run the cell. And there we go. Everything's happy now. So we've got a blank cell there. Here we've got the predict. I don't know what that is. Everything's going over my head. We've got dot shape, another prediction there that just went through, didn't output anything. Dot shape again. So yeah, everything's kind of over my head. This dot head should show the first few lines. So there are 50 epochs, so I'm not sure what we're seeing here, but I'm sure we're not seeing everything. So now here's a graph like we saw before. So we're just kind of printing out the same things. And here's that final graph where it's just pointing out the maxes. So it's like not doing it right according to the book, which is kind of not good. But yeah, I'm really happy with this. I got everything to run. I got all the graphs to display. I even got an accuracy number to print out that was significantly higher than what was shown. Whether that means that's good or bad, I don't know, but it's hopefully good. So that's it for this video, and that's it for use case 1. So thanks for watching, and stay tuned for use case 2.